All right, so let's look at some information about titrations. All right, titrations are going to be basically an application of acid-base neutralization reactions. So you got acid plus base is going to make a salt plus water, and you use an indicator. It is a technique that allows us to have a solution that we know the concentration of, and then we use that to determine the concentration of an unknown solution based on some stoichiometry calculations. If you are trying to find the concentration of an acid, you would titrate that with a base that you know the concentration of. And if you were trying to titrate a base that you didn't know the concentration of, you would do that with an acid that you did know the concentration of. So you either have to know the concentration of the acid or the base, okay? And then you're trying to find the other one, whichever one you don't have. All right, some terms. Equivalence point is the spot on the titration curve where it is the exact stoichiometric amount needed for acid and base to completely neutralize each other. It's the steepest part of your curve. So here's a titration curve, and the steepest part, which is right here, is going to be your equivalence point, because so that's when you have the just right amount of acid and just right amount of base to cancel each other out and make a salt and water. The end point of a solution is going to be, or a titration, is when we actually see with our eyes the indicator change color in the lab. That may or may not be the same as the equivalence point, just depending on what indicator you chose. If you don't choose the correct indicator, your end point could throw you off some. The half equivalence point is exactly what you would think it means. It's the half of the volume of, like in this picture, it'd be where half the volume of base that is needed to reach the equivalence is located. So basically half the acid or half the base is titrated. So you have half and half at this point. So you have half protonated, half unprotonated. That means that the pH equals the pKa. You don't know what all that means yet, but it'll be important eventually. And that is the flattest part of the curve, so right here. A buffer region is a region where the solution resists a change in pH. So you see here in this lower region that, it's trying to stay flat, so it's resisting a pH change. And then when we say pKa, we're basically just saying take the Ka value for that acid and take the negative log of it, just like we would the H plus concentration to get pH. You can take the negative log of the Ka, and that'll give you pKa. Okay, it just makes the number easier to use because it makes it a number between 0 and 14. All right, so when you have a strong acid, strong base titration, you're going to have, a slow change and then a very quick change, and then again, no change again. So this would be a HCl and an NaOH solution. You see that they are both strong. And that means that the pH at the equivalence point, where you have just the right amount of acid to neutralize just the right amount of base, would be pH of 7. All right, now that should make sense because they both dissociate completely, the strong acid and the strong base. And remember, when you have a strong acid, strong base, it makes a neutral salt. So that would be pH of 7. All right, the steep rise in the pH is where the acid, is where the H plus ions from the acid have been completely neutralized by the OH minus ions of the base. So this is where the curve flexes, and that's where we say the equivalence point is. And remember, it's at a pH of 7. Okay, here's a molecular view. So we see that initially we have some H pluses, and then at equivalence point we have H pluses and OHs making water, and then here's our salt, our Na and our Cl dissolved. And then when you get beyond the equivalence point, you have an excess of base, so you have more OHs than H2Os. All right, now if you go the opposite way, if you take a strong base and titrate it with a strong acid, you'll get the exact same curve, except it'll be reversed, it'll be flipped. So here you have starting with a strong base, and then it neutralizes, and then you have excess acid over here. pH at equivalence point is still going to be 7. All right, so basically, to do calculations for these, to calculate the volume of base that you would need to reach the equivalence point, you're just going to use M1V1 equal M2V2. There are 3 different situations in which you would need to determine the pH to get the titration curve of a strong acid, strong base titration. So initially, if you wanted the strong acid concentration, that would just be the negative log of the acid concentration, because we know that the acid will completely dissociate into H plus ions. And then at equivalence point, we would want to know the pH, and this is always going to be 7 because it's a strong acid and a strong base. And then before the endpoint and after the endpoint, so there and there, you could calculate the pH by calculating the moles of excess H plus or excess OH minus ions, dividing by the total volume at that point, and then that'd be your concentration of H pluses, and then you could negative log that to get the pH. Okay, so those are the things we're going to need to do to get us a titration curve. Okay. All right, so let's look at this one and try to draw a titration curve. Okay. All right, so here we are asked how many milliliters of 0.1 molar NaOH is needed to titrate or neutralize 20 milliliters of 0.225 molar HCl. Okay, so basically we're looking at an M1V1 problem. All right, so this is the first concentration. So we have 0.1, and we're looking for the volume of that we would need to neutralize this second concentration of HCl, and we have 20 mils of it. Okay, so when we work this out and solve for V1, I get 56.25 milliliters of NaOH would be needed. Okay, so that's the total volume to get to equivalence. All right, it didn't ask me this, but I'm going to sketch a little bitty titration curve, not super accurate, but just to get us thinking about it. So I'm going to find the pH of the initial solution. Okay, so we have a 0.225 molar HCl solution, so that means we have 0.225 molarity for H plus as well, negative log it, and our initial pH is 0.65. All right, so now let's sketch just a very, very rough titration curve. So here we got pH, and this is NaOH milliliters. All right, and let's see, we'll call that 1. So we know that we start below 1. We have a buffer region, then we have a quick increase, and then we narrow. All right, so here is our equivalence point, and we know that for a strong acid, strong base, the equivalence point is always going to be at 7, and we know that the volume of that base that was added to get to equivalence was 56.25 milliliters. Okay, so that's just a little bit about strong acid, strong base titrations.